My turn then? Okay. Well, hello everyone. I'm Patapom from Bomb. I'm going to try to talk to you about real-time volumetric rendering. It's kind of a huge topic to cover in such a short time, but don't worry. There's a companion document PDF that's available at my website with plenty of details, shader code, and everything that you need. Let's go. So rapidly, we're going to try and render what we call a participating medium. It's basically a volume in which particle density or refraction, albedo, many properties of the medium change quite locally. So due to that local change in properties, we're going to need to use remarching. Many of you are familiar with remarching, like distance field and stuff. And instead of sampling distances to objects and things, we're going to sample particle density or incoming light at a particular position inside the volume. What's going to happen to the photons that travel through the medium is really rather absorption by the medium or scattering. And scattering comes in two flavors, the good one and the bad one. I mean, the bad one is outscattering. That's going to diminish we're going to have an energy loss due to photons that are initially coming in the view direction and bounce off of particles in another direction, so it's a loss of energy. And there is another type of scattering, which is very interesting, which is the in-scattering, and this is the opposite. You have a particle photon coming from any direction that finally bounces off into the view direction. And this actually adds light, contributes to adding light to your path, to your ray. So absorption and outscattering are combined in what we call extinction. Extinction is given by the Beer-Lambert Law, and we see that it's an equation with an exponential and sigma t, which is the extinction coefficient in meters or reciprocal meters, and it's the sum of sigma a and sigma s, which is the absorption and outscattering coefficients. And we see that the exponential also depends on the distance. It basically means that the more you travel inside a medium, the probability of hitting a particle and having extinction grows exponentially. So that's for extinction. Now for in-scattering, we're going to use a phase function. This one is dependent only on the single angle called the phase angle, which is the angle between the light and the view. And it's going to basically give us the probability of a ray coming from any direction and being reflected into view direction. It's kind of the equivalent of BRDF for standard materials. In the sense, it's kind of a black box that tells us how the light interacts with matter. In this case, dust particles, water droplets, water particles, anything. Obviously, what's happening inside a real cloud or real smoke is very complex to modelize. So we're going to break up this complexity using several simpler phase functions shown on the right, like any Greenstein or relief phase function, which are kind of easy to compute. And we can combine them using a weighted sum of any Greenstein, for example. And you have some sort of multi-lobes phase function, which is kind of okay for demo effects, I suppose. So now the real deal. So we have this equation, which is the light transport, volumetric light transport equation. On the left, you have the radiance, L, at a given distance, and omega, which is the direction of our ray. And you see it's an integral, and from 0 to the length of the path, which is d. And in green, you have the extinction we talked about earlier. And in red, this is the meaty part. There is a inner integral that tells us that we have to actually account for light incoming from all possible directions. And you retrieve the phase function with omega prime, which is gives us the phase angle. And this phase function multiplies another radiance, which is the incoming radiance from all possible directions. And unfortunately, this radiance also uses that same integral. So it means basically that it induces recursion. And every new recursion step uses that computation. It's kind of prohibitive to use in real time. But every time you recurse one step, you account for a new, higher order scattering event. So this is called multiple scattering. Obviously, you can't do that in real time, but we can take simplifications like using only a single light source, the sun usually, and we can approximate the higher order scattering events by the well-known ambient term that we use quite everywhere. Instead of computing global illumination and direct lighting and stuff, it's kind of basically the same thing. So you get this integral, which we got rid of the inner integral. That's the first step. And what next? Next, what you need to solve that integral, you need three things. You need to be able to sample the medium at any position to get the density, so you can use a 3D texture or any IQ's secret recipes, and combine this using fractional Brownian motion, which is kind of the best look you can get for clouds from my experience anyway. And using that density, you can obtain the sigma S and sigma T that you need in the integral. Next, tricky part, but kind of okay. You need to be able to also get the incoming light direction from any position within the cloud. So it relies on the volumetric shadow map that you can use several known techniques like deep shadow maps or transmitter and function maps. These ones are really great. I tested them quite a few weeks ago, and so it gives great results. And finally, the cheap ambient term, but that works quite well. You can see I don't know if you can see the difference, but it's kind of dark, and with the ambient term, you get a sense of a little more realistic rendering. And finally, you can use that in the discretized integral that transforms into a sum of n steps and familiar steps of remarching. And you see that the extinction has been extracted from the integral, the sum, sorry. And it's now a multiplicative series where each new term multiplies with existing extinction. And this means at the end you're going to use this. To use this as a transparency for the background. And finally, the algorithm is quite simple. You compute arriving light incoming at a given position, and you multiply it by the extinction along the path, and you repeat this for each new step. And in the end, you just compose with the background, multiplying the background by the extinction and adding the incoming light. And that's the pre-multiplied alpha blend mode that some of you may have tried already. And that's all. It's basically just a quick video. I don't know if I have time, but I'll try. Where's my cursor? Yeah. So this video is from my plugin for Unity called Nuage, which is cloud in French. You see it can simulate up to 4 different layers of clouds, 2D layers, 3D layers, fog, It manages time of day, satellites, light by moonlight, pretty much anything. There is a storm here, you can fly through the clouds. And it runs quite well, actually. I have a crappy PC here, and it was working at 50 FPS, and it's kind of okay. Well, that's it. Oh, the video is quite laggy. So that's it. I'm going to cut the video. You can find the video and everything, the document, and this presentation is available at my website at patapom.com. Well, enjoy and create some great volumetric effects. Okay. We have time for questions.
Tests 1, 2. Yeah. In the normal distance field ray marching that's employed in the demo scene, your step distances are not constant, whereas for volumetric ray marching, you'd want that. Do you know any good tricks to combine that?
Not constant step marching in. It's kind of difficult, actually. If you look at Jensen's publications, he advises to use the log of the density to make your step actually vary. Mm-hmm. And I tried that. It is complete crap. But I think I didn't. I didn't understand very well. But I think it's okay for offline rendering. Yeah, perhaps if you have many rays and perhaps it ends up correctly. But I don't know. No, you don't agree. It doesn't.
It doesn't. Yeah, we've tried. So.
No, you just.
Okay. Yeah.
Okay. Another question over there. Okay, with raised hand.
Out of time. Out of time.
Okay, hello. I'm Seven from Fulcrum. I released my slowest ray marching 4K yesterday, so now I'm going to talk about making ray marching 4Ks faster. And it doesn't want to go. No idea what. Okay, so you have some very expensive distance function for an interesting object. Don't use that if you are a million miles away from it. You can use a cheap bounding function. So first you calculate the distance to the cheap bounding function, and if that's close enough for some value, then you use the more expensive function. So for this scene, which has a C with 4 octaves of noise, simple bounding planes makes it 70% faster for only a cost of 9 bytes after Crinkler compression. So that's pretty much worth it. This Mandelbulb sphere can be put in a bounding sphere. That's 35% faster for 12 bytes. Okay. So the good points are that it's cheap and it's simple. The downsides are that you have to add a bounding function per object. It only helps if your starting function is expensive enough. The more expensive, the better, of course. And as soon as you want to move your cam inside your object, then a bounding function is not going to help you anymore. Something I learned from Rola's Boxplorer is overstepping, which means that you step a bit further than your distance function says is safe. And if you end up inside your object, you go back a little bit. You can vary the amount of overstep based on the optimal length of the previous step. Boxplorer is open source, so you can learn from that. It's not that much faster. In Boxplorer, if you remove the overstepping, it's only a few % slower. When I tried to use it on a certain 4K, it was actually slower, and it takes about 70 bytes. So I wouldn't use it unless you really want the highest possible speed for a specific function that you want. But it's fairly big for a 4K, and if your objects are really, really thin, you can step through them. This happens especially if your distance function is not signed distance function, but unsigned. If you have a plane and you have positive values on both sides and you step through it and you don't notice and you just continue marching and you have holes in your objects. Nysteps had a kind of cone marching before I knew it, so I used this term for it. But it's described in a poet thread, trick for 1K ray marchers. And the idea is that you, instead of tracing a line, you try to trace a cone. And when you get further away from the camera, you make objects easier to hit, both by making your hit distance larger. So when you stop tracing when the epsilon is larger and larger, and also by making the object itself bigger. You really you have some line of code like distance equals distance function minus epsilon. And I had a hard time getting the results Nysteps described. It really depends on the scene and especially the complexity of the faraway background. So on this scene, I got a 50% speed up for only 50 bytes larger. This is the best result I got. So it's cheap, and for some scenes, I think it's really worth it. But on the most scenes I tried it, I didn't really have an effect. And the problem with stopping tracing when you're a bit away from your object is that your normals get inaccurate. So at large distances, especially if you have reflections, you start to see strange things. My cone marching seminar from last year can be found on YouTube. There are slides. So it's a kind of multi-pass, low-resolution pre-color distance finding. I made this invitation intro both in a 4K version and a non-compo version with cone marching. And for this seen it was 88% faster, but it's 348 bytes larger, which is painful. So you have a good speed up, especially if you have expensive functions, but yeah, 350 bytes. It only accelerates primary rays. If you do reflections or soft shadows, forget it. And you can't do certain per pixel effects because they become blocky or just plain impossible. So just scene fades from in hard verdrahtet, where some of the pixels show the current scene and some of the pixels gradually show the next scene. You can do that if you try to use 16 by 16 blocks of pixels. Yeah, I suppose most people know this, but if you're a beginning 4K coder, modern cards are so fast that you can put your entire intro in one big shader. And then you reach a point where you add just one tiny line and suddenly your frame rate drops a giant amount, no matter what you are changing. Which means that your card has run out of some internal resource, probably registers, and it cannot use all the shaders at the same time anymore. And since your shaders are kept in blocks of CUDA cores or whatever, then it starts to remove a shader from every core and you lose a lot of GPU power at once. So solution, which I first saw in muon baryon, is to split your shader in one common part with a marching loop and shadow and reflection stuff, and then some per scene parts like the camera motion or the scene distance function. And when your intro launches, it stitches them together in a per scene shader. So when you reach a new scene, you switch the shader. And often that also means you can simplify the script in the shader, which offsets the extra work you have to do and the extra byte your launch code takes. I actually tried that for my intro last year, which made it 20% faster, but yeah, also 80 bytes bigger right before the deadline. So yeah, not in the final version. So the nice thing about this optimization is that this speed up can be combined with every other one. It's completely independent from it. You get the combined benefits. And if you have a scene an intro with lots of small scenes, then shader stitching can actually be smaller than using one monolithic shader. The downsides are that you get the biggest effect on older cards, which had less registers, and you have to rewrite basically your entire shader. So it's not really it's not something you can easily add afterwards, like in an hour before the compo. So yeah, so far the random collection of techniques. Are there any questions?
So you mentioned that the stitching part was orthogonal in a speed sense, but how do the other methods do they compound the speed up, or are they sort of separate things that you can only really get a good speed up of one of the methods at a time? Or
I'm sorry, I didn't quite.
So the question is, do the other methods, do their speed ups compound? Do they get increasingly faster?
It depends on the methods and the objects. For example, the bounding box accelerates only the first part of your array, and the last part is difficult. The cone, my cone marching, also accelerates the first part of the array, and the closer you get to the object, the higher the resolution you have to render it at. So I think that bounding boxes and cone marching are not going to get a combined result. Yeah, it depends. You have to think a bit about it. Also differs between simply distance functions that are inherent expensive and you have distance functions that are unsafe, but that you have to use a safety factor, that you can only march like half the distance, that also adds, that makes the function more expensive, but that one can benefit more from things like overstepping or cone tracing. So yeah, it depends a bit.
Talk a little bit about DMX. I'm from Holland. We have outline, and I make demos for that. They look like this. But I also do a lot of light stuff for big parties, smaller raves. It kind of depends. Squad parties as well. Theater festivals and art festivals as well. Odd installations like this one. Also do like big commercial projects like André Rieu. He uses a lot of snow, for example, and you can imagine what happens if you put snow into a light. That's not a big idea. Sensation White is other stuff I'm involved in. They use a lot of, this is Sensation White, a lot of balls like this. And some of fact, they're actually like inflatable balls, and they pack them up in a truck, and you can fit like thousands in very small space. So it's very practical. With all the big festivals, I'm mostly doing stuff like this, so there's not really that much of creative stuff involved in doing festivals like this. So DMX 512 is basically a protocol for transferring lights. Back in the early days, you had a lot of different steps that you need to go through from one provider, from light fixture to another. And even within the same provider of fixtures, you probably had to use a lot of gear like that. So you had the club scene and the theater scene both struggling with the fact that you had so many different adapters all chained into each other. It resulted in a big mess. No one was able to really take a step forward to make some more complex, nicer shows. So they all came together and they drafted DMX, and trying to get rid of stuff like this. It stands for Digital Multiplex with 512 pieces of information. Martin is a company that in 1986 DMX was drafted, and they keep on running their own protocol around 1996 when they gave up. So there are a lot of fixtures still sold with the 512 lookalike connector, but a completely different protocol, which is not odd that they're so, in their own way, they're based from Denmark. But you can buy the stuff that looks like DMX on eBay still today, so it's kind of annoying if you expect it and you don't get it. This is the protocol itself. I won't go that much in depth into it because I'm already running late. So it looks like this. But you mostly look at it like this. This is a DMX universe. I'll get back to it later. This is a light controller. Costs like 40,000 K. Same as the thing back there. This is a DMX USB controller. It registers as a virtual COM port device for the musicians out there. You might know if you got like a MIDI device, a MIDI USB, it uses like a virtual driver as well for using the MIDI. This is DMX for you. It's a kind of dodgy URL, but it's rather cheap. In my example, I'm going to use that. If you got more budget, I recommend Numtek, or if you got even more budget, the Lambox. Don't buy the Velleman and don't buy the Numtek Pro Open because they're like depending on your CPU for the speed and frame rate. So if your CPU glitches, so will your lights. It's not handy. DMX start address. Every fixture has a start address that you need to set with dip switches. They look like this. You can flip them and then set the channel where it starts. Luckily, software has also built-in like calibration tools to help you out, so you don't need to calculate them all. If you buy newer fixtures, of course, there's no dip switches involved, unfortunately. And yeah, you can just program it in. Ah, too late. Okay, well, this is, I'm just going to continue on. More complex fixture. As you can see, it has a lot of options. It can tilt, it can shift, it can pan. It has a lot of colors, it has a lot of gobos. Gobos are go before optics, so they project nice shapes and forms. You can shut it and dim it. So this is the implementation chart of it. So yeah, a lot of stuff. If you use it in a universe, it takes up this amount of channels, whereas this small LED one just uses 3 channels. So if you go like faster and bigger, harder part is more gear. Stuff like this, it's a green hippo. It takes up 122 channels, and that's just one mode. If you switch to another mode, it will take up your whole universe at once. So start address amount of channels. Another point that I'd like to point out, if you got like the data sent over the DMX and you drop a frame, it will like sample and hold. So it will continue with the last known digit until it reaches a new signal, and it just continues on where it left. So all data is broadcasted each frame through DMX 512 is sent through DIN5. XLR, it looks like this. Or, yeah, this is a Nysteps Ethernet connection. A little bit about the cable is you can buy XLR cables which look like DMX, but they're audio cables. They got a different capacitance, so they're not suitable. Network topology is linear drop bus network. It's unidirectional, so it goes like one way. To illustrate, one fixture breaks. Everything in the chain that goes after it will break. So if a device is a single point of failure, you got splitters if you want to fix that. So you can make different network topologies where you got a lot more redundancy. And so if one fixture breaks, it won't take out the whole chain afterwards. Another trick that you find a lot in the professional entertainment industry is using multiple universes. So if one universe breaks down, or part of it, other universes won't suffer. So you see that the rest, yeah, well, they survive. Yeah, multiple universes. A little bit about the safety protocols. This is a laser that you can buy. It's like consumer grade, but it could end up hurting people if you look at it in the laser. But it goes on DMX as well as this one. And Pyro shows stage flames. It has DMX. It has no error checking, so if you send a signal over the wire, 3 minutes? Okay. Well, that's fun, okay. I'll just continue on with the demonstration. Oh, this is awesome. This is Freestyler. It's a DMX software. And if you give me 1 second, see, if I click here, you'll notice the light going on. And if you can point it, and it will go to where the, oh. So yeah, you also got, this is not really working, but if I execute a sequence, you'll notice it will go on. Okay. 1 second, and I'll get back to the talk itself. Yes. Okay, no error checking. Yeah, this is an example of 360 tour. It's quite big, use a lot of channels, this one as well. And this is Olympic Games. You can use it for water as well, since it's quite safe. Rain doesn't matter, and it can handle it all. Snow, no problem. Even if it's like temperature in the tropical range, it will survive. Robust, stable, scalable, I mean, tried and tested. Using it basically everywhere. I'll go through this really fast. You can read it yourself, so there's possible software that you can use. Arduino could also send out DMX. Resolume, okay, one point, if any of you visited Max MSP workshop by JCO, imagine what you could do if you combine Arduino with MSP or MNUX. Basically, yeah, anything that you can imagine with lights going on and off. Yeah, it's possible. Reno is, I use it for sequencing DMX. Yeah, this is a little bit about the difficulties in handling larger projects like these people do. Yeah, it gets more and more complex if you have more stuff, and it results in cables all over the place. But you have technicians to help you out with that, and they're very helpful. So, this is the future. MIDI show control, it might be the new standard, or architecture for control networks, or ArtNet. Yeah, basically, since DMX is so old, drafted in 1986, it won't last that long. But yeah, some standards that will have to evolve will have to be always downwards compatible, since there are so many fixtures like this all over the world. There's no way of like giving up on the protocol completely to do stuff like this. So yeah, that's the big light that you see in the main hall. It's also on DMX. So yeah, give it a look once you're there. I would say time for questions, but I think anyone got questions?